Hello guys, so with this video we will get started with hydraulics and we will cover the calculations in this topic. So I want you to learn it, I want you to listen it very carefully because it will be in the test, and the calculations are very difficult in hydraulics, so you have to understand how to calculate all these things, because it will be a very important part of the test. So let's get started and let's get into the power converters, because we will calculate the power converters today. So basically in hydraulics the medium is much more different than in pneumatics. So basically in hydraulics we will use liquids as the power medium, and therefore the power medium will be uncomprimed. So we can't lower its volume. Okay, so we can't we can pressurize it, but we can compress the medium. The other thing is different from pneumatics, that the hydraulic oil or hydraulic fluids are much more dense than air, and therefore they have a much bigger viscosity than air. Therefore the losses are much bigger due to its property, because if you have a viscous liquid, it is much more hard to press through a little pipe. Okay, if you can imagine, if you want to push fat or into a tube, it's much more difficult than push for example water through. Okay, because this fat is much more viscous. So simple is that. So let's see the losses of power converters. So in the ideal world we wouldn't have any losses with fluid techniques, but we are not living in an ideal world. So we have two basic losses in hydraulics. These are the volumetric losses and the hydromechanical losses. The volumetric losses are due to the operationing CPGs. So there are some CPGs near the moving parts of the pumps and motors and pistons and whatever. So therefore we have some volumetric losses. So not all the fluid will make some work, but a little amount of oil or liquid will go through these little creepages and will cause a little seepage, and therefore this is a loss. The other thing is the hydromechanical losses, and these are the losses which are converting the energy what we are putting in the system to heat, basically. So these are the hydromechanical losses, and therefore they will heat the oil up. And this is a real problem in hydraulics, because the hydraulic media, which is basically some liquid, it's fairly usual, it's oil. So the oil is degrading at 80 centigrade, and therefore if we have a bunch of hydromechanical losses which are heating the oil, this temperature can be easily exceeded. So therefore we have to calculate this type of losses. Okay, but first thing first, we will look at the pumps, how the pumps can be achieved, and we will use one type of them. But first things first, here is the pump symbol. Okay, it's fairly easy because we saw that in pneumatics. It was the compressor. The triangle was white in it, but in hydraulics we can show it that it's a hydraulic pump, that the triangle is black altogether. And we have a hydraulic motor here which has another triangle, but this triangle points inward the device, so I know it's a motor which will which will convert the hydraulic energy to mechanical energy through this shaft. Okay, so fairly easy. But how can we achieve this hydraulic energy? How can we make this hydraulic energy? We have to use pumps, and we can use a bunch of pumps which are all drawn with the same symbol here. Okay, so we can use cog pumps, which are using basically cogs to transfer fluids, and the fluid will transfer here. Okay, here and here in these little indents of the cogs. Okay, so not here. In the ideal world, here is the how to say it. So here's the seals or gaskets are ideal, so they can't let any fluid backwards. But we are not living in the ideal world, so there will be at least some seepage here and here as well. So through these creepages, where the effectively the mechanical parts are moving. Okay, we have the vane pump here. We have the inclined disc, which is fairly commonly used in older equipment. So, for example, in the air conditioning units in cars. But nowadays we are using electrically actuated pumps. So therefore, these are used nowadays in hydraulic applications, which are the torque sensitive or load sensing applications. Okay, and the radial piston one, which is this, but we will use the cock pump because this cock pump is this is the carefree one. Okay, it's fairly cheap, it's fairly easy to maintain, and it's good altogether because it can be used as a pump, it can be used as a motor. So usually we use cock pumps and cock motors in hydraulics, but yeah, we use all of the types, but these are the much more common types. Okay, let's go a bit further. So what are volumetric losses? Volumetric losses are the CPGs basically. Okay, so here we have, you can see here we have a little, how to say, creepage. So this creepage is basically the operational gap. Okay, so this gap have to be here to make it possible to rotate these cogs. Okay, because if we don't have any gap, that means I have a solid piece of metal here, and therefore we can't rotate the cogs in it. Okay, so therefore we have a gap here, and this gap can cause a little seepage. Okay, so fluid can go flow through here in the back direction, as well in here. So basically volumetric losses are these. These are the losses that are occurring while the fluid is not going in the right direction. Okay, volumetric losses can occur in a bunch of hydraulical how to say, energy converters. So for example in cylinders as well, because we have an operational gap or creepage here as well, and therefore if we have a big enough pressure, oil can flow through these creepages or operational gaps, and therefore it will be cause a leak or seepage in that direction. So not all the hydraulical fluid will make the cylinder move, but a little amount will flow through here, so basically near the seals, and therefore it will not work. Okay, so it's a loss. The hydromechanical losses are the losses which are converted to heat. So for example, flowing through a throttle valve is a hydromechanical loss. So here the loss of energy will convert it to heat, and it will heat up the fluid and heat up the entire system. So therefore we have to calculate these power losses, and we have volumetric loss, we have hydromechanical loss, and we have overall or resulting losses, which are the power losses. Okay, so these are volumetric loss, these are energy loss, and these are power loss. Okay, so if we have losses, we can determine the efficiency of the devices. So we have volumetric efficiency, hydromechanical, and overall efficiencies. Okay, and in the case if we have hydraulic pump, we can calculate these efficiencies. But first things first, we have to cover what is geometrical volume. Okay, so VGS is the volume, so the volume that the pump can provide in one revolution. Okay, because we have a rotary engine here. This rotation will be transferred to how to say to flow rate. Okay, so one rotation will provide that much liquid to flow. So therefore, if I want to calculate the geometric flow rate, okay, so the theoretical flow rate in our case, I simply can multiply the n, which is the revolution per minute, with the geometrical volume of the pump. This data here is a given data, so we can read it in the data sheet of the pump. The n will be provided by the motor, so for example electric motor, and therefore we can read the data sheet of the motor, and we know how much revolution it can provide in a minute. Okay, and therefore we can calculate the theoretical flow rate of this pump. But we know that we are not living in an ideal world, and we are not how to say calculating only the theoretical things, but we want to calculate the actual things. So therefore we can use some mathematical magic to calculate the volumetric and hydromechanical efficiency and the overall efficiency as well. Yeah, it's a bit ugly here, because this equation is not so beautiful, but if you understand how it works, it will be much more sympathetic. Okay, so eta Vs is the volumetric efficiency of the szivattyú, which means in Hungarian pump, so therefore Vs. So the volumetric efficiency of the pump is equals to Qs, which is the provided flow rate divided by the theoretical flow rate. Okay, so I can measure the flow rate which is provided by the pump, and I can simply calculate how much it would be theoretically provide. And if I have a smaller number in up here, and I will divide it by a little number, or sorry, a bigger number, it will be resulting a number less than 1. And because nothing has more than 100% efficiency in the world, therefore we have to calculate less than 1 in our cases, because if you calculate more than 1, then you will reach a Nobel Prize, or you will get in the Elysium. Okay, second chance, the chances are second is better, yeah. So therefore we have to calculate the hydromechanical efficiencies as well, and the eta hydromechanical for the pump is calculated by this equation. This equation is also very ugly, but if we can understand it, it will be much better. So I know that I have to put more energy in the pump than the pump can provide in the hydraulic side. So therefore I know that this part here will be the smaller, so it will be the smaller, or the actual energy what the pump providing. And here this is the mechanical side, in which we trying to put in energy in the system. So therefore, if you can remember, you can calculate the power in mechanics with m times omega, and omega in our case is 2pn, and 2pn is a fairly interesting thing, because 2pn will provide us a number in watt seconds. Okay, so basically power. But now we will not write here n, therefore we will calculate it in energy. Okay, so joules. In hydraulics, in the other hand, we can calculate the power with the how to say, with the equation P times Q, and because Q is N times Vg, therefore I can write here N and N, and I will simplify the equation like this. Okay, so these are not power, so not joule secundums or watts, but energy, so joules. Okay, but because it will be so it will be a ratio, therefore I can use this equation. Okay, and the overall or resulting efficiency is this, if you like, but if you don't like it, you can simply use this equation here. Okay, so you can calculate these two, and you can simply multiply them, and you will receive the overall efficiency. So it's very simple. Okay, the hydraulic motors, which are almost the same, but you can easily understand that if you have a hydraulic motor which will provide mechanical energy based on hydraulic energy, you have to take you have to put more hydraulic energy to receive the same energy in the mechanical side. So therefore here the equations will vary a bit, but only the top side and the bottom side will change directions. Okay, so here we can calculate the theoretical consumption of the motor, okay, with the geometrical volume and the required RPM here, and the volumetric efficiency will be here, that what we provide for the pump. Okay, it will be bigger than what the pump actually provide us. Okay, so if I calculate the how to say, the theoretical consumption of the motor, then it will be a smaller number than the actual consumption of the pump. So therefore we can measure the inflowing liquid, so the flow rate, which is here, and we can calculate the theoretical flow rate, which is here. Okay, and it will result a number which is less than 1. The hydromechanical efficiency is a bit different here. Okay, let's see. So the hydromechanical efficiency, I know that I have to provide energy or power to the motor via hydraulics, which will be bigger than the mechanical output. So therefore the ingoing energy has to be more than the outgoing energy. Okay, the ingoing energy can be calculated with P times V, because if you remember, the power of the hydraulic was P times Q, and now we use the same N, okay, so the same revolution per minute, because the revolution is the same here. Okay, so on the shaft of the pump or on the motor is the same, so therefore we can let them go. So now we can calculate with energies. So the output energy is calculated with the torque, which is outputted in this shaft, and 2P, okay, because it's a rotary machine, and the ingoing energy of the motor is calculated with delta P. Delta P is the difference between this and this, okay, delta P, which is making the fluid move, times the geometrical volume of the motor. Okay, and the overall efficiency here is also can be calculated with this simple equation here. Okay, it's very simple. Now if we go further a bit, we can discuss the efficiency of hydraulic pistons. So the pistons are very alike to pneumatics. Big differences are in the piston rod diameter, because we can utilize much more force with this type of cylinders, so hydraulics. Therefore the buckling of the piston rod is so the possibility of buckling this piston rod is much higher. Therefore we have to use a much more thick piston rod, and therefore the difference between the areas in the positive and negative chambers are very big in this type of application, so in hydraulics. So therefore we have to calculate these as well, and we will make some calculations with this. Okay, so in the test there will be a bunch of exercises, bunch of calculations, so therefore we will cover them. So what are the most how to say important things in pistons? So the stroke length, the force which can be actuated in the positive direction and the negative direction, the maximal pressure which can be utilized with these type of cylinders, the piston diameter, the rod diameter, and the maximal traveling speed. Okay, so how can we calculate the efficiencies? We have here volumetric efficiency here. Okay, and we know that okay, so let's get started here. So if I want to calculate the speed of the piston, how can I do it? I can do it with this equation, Q per A. Am I right? Because Q is in cubic meter per second, and A is in square meter per second, and if you per second, so if you divide cube meter per second with a square meter, you can receive a meter over second. Okay, so here we can see this. Okay, so therefore Q equals A times V. Okay, so here we can see this. So the volumetric efficiency of a piston is the measured ingoing flow rate, okay, which is bigger than the theoretical flow rate, which would be this. And if I divide a little number with a bigger number, it will be less than 1. Okay, and this is correct here. So the hydromechanical efficiency is this, because if you remember, we can calculate the power, the force. So F equals A times P, where A is the surface of the piston and P is the pressure which is acting upon this surface. Okay, so therefore if I can measure the force which the actuator is providing us, it will be a smaller number than the theoretical number, because here are frictions and here are friction and so on. So therefore I have to provide a bit more energy to overcome these frictions. Okay, but this energy will be converted to heat, okay, because friction is converted to heat, and the overall efficiency is easily calculatable with this equation here. Now if we go a bit further, then we can see the main characteristics and parameters of hydraulic pumps, and these are not very interesting because we covered these in the previous moments. So therefore we will calculate some real examples. But now I will run through these slides. You can always stop them, and you can how to say, learn them if you want. But if you understand how to use these equations, you can make your own equations. Okay. Okay, it is important now because it could be in the test. So this is a hydraulic power supply unit, okay, or pump unit. This pump unit is built in this way. So we have a tank here. Okay, we have the pump itself, the driving motor of the pump. We have here a filter. You have here a manometer. The pump unit has two outputs, one pressure output and one tank output. It's an input, to be honest. So the flow will go flow through here. Here is a device, for example a motor, and the liquid will come back in the tank in this connection. Okay, here is a pressure relief valve, which is important because if we have a constant N here, or how to say, revolution per minute, and we have a VG here, which is also constant, then we have a constant Q constant flow rate in here. And if I have not a motor, but for example a piston here, which is provided by this, like this, okay, then the piston will move in the positive direction. And if it reaches its positive direction, so here, then the piston will stop, and here a very big pressure will be accumulated, because if we have a constant Q here and it can't flow anywhere, the pressure will rise, and in the end of the day there will be a rupture in the pipeline or whatever. So it's a very uncomfortable thing to have. So therefore we have this pressure relief valve here, which is providing a security, or not security, how to say it, a safety role. So if the pressure is too large here, then we have this control line here, and this control line will force this valve open, okay, and then the oil can flow through this pressure relief valve back to the tank. Yeah, it's a very big loss, so it will constantly hit our hydraulic fluids, but it has to be in these systems. Yeah, we have some load modulating technologies available, but these are very how to say, costly, so therefore we don't use them in general. Yeah, we have some fields where we use them, but in general we use the pressure relief valve method. Okay, okay, and now we will make some calculations, because we are there now. So we will use this little sheet here. Okay, so we have a hydraulic pump which has a geometric volume of 23.4 cubic centimeters per revolution. The revolution which is provided by the motor is 1450 1 per minute. I know the volumetric efficiency of the pump. I should maybe zoom in. It's 93%, and the hydromechanic efficiency is 95%. The questions are: how much is the pump's theoretical delivery, and how much is the actual delivery of the pump, and how much is the total efficiency of the pump. Okay, so we have three questions here. The solution is fairly simple. The theoretical flow rate is calculated by this, as we covered, and I converted the VGS to decimeter, cube decimeter. Okay, because 1 cubic decimeter is 1 liter, so therefore it's much easier to use that calculation. If you want, you can always use SI, but in this case I think it's much more easier to use directly liter as the geometric volume. Okay, so therefore we can calculate it directly in liter per minute. The real is a bit off of this, so the real is the theoretical, sorry, I forgot to, so the theoretical times the volumetric efficiency. So the volumetric efficiency only has an impact on the flow rate. Okay, and the hydromechanical is only have an impact in the mechanical things. Simple as that. And the sum or total efficiency is these two, where are they? These two multiplied. Okay, very easy. Second exercise is not so easy anymore. So we know the following details of a hydromotor. The geometric volume is 100 cubic centimeter per revolution. The revolution is on the output shaft on the motor is 250, 1 per minute. The volumetric efficiency is 95%. The hydromechanical efficiency is 82%, and the output torque is 180 Newton meters. Okay, so how much fluid should be pressed into our motor? This is one question. And what is the pressure that is required to deliver the torque to the load torque? So what will be the pressure drop on the hydraulic motors? And we can calculate this like this. Okay, so the ingoing flow rate should be calculated with the theoretical flow rate divided by the volumetric efficiency. That's because if you divide a number with a number less than 1, it will result a bigger number. Okay, and we have to make more liquid flow through this motor to achieve this revolution. Then the needed pressure difference here is calculated with this. So I know how much is the needed torque, which I have to give on the output, which is 180 Newton meters. I have to multiply it with 2p, and I have to calculate the how to say it, the pressure difference, which we can be achieved with this. Okay, so basically I have to divide it with the geometric volume, and I have to multiply this geometric volume with the hydromechanical efficiency, because it is now a mechanical thing. Yeah, so the torque is mechanical and the pressure in our case is mechanical. Okay, so this is the flow rate, and the flow rate and the volumetrical efficiency is going together, and anything mechanical will go together with the mechanical efficiency. Okay, so not combined. And the sum of the efficiency or the total efficiency of this motor is calculated by this simple multiplication of the two. The third exercise is a bit more difficult. Okay, so we know the following data of the double acting single roded cylinder. We have the piston diameter, the piston rod diameter, the volumetric flow rate which is entering in the cylinder, and the force should be applied by the cylinder. So the load force should be 50 kilonewtons, and the force needed to overcome friction, so all the mechanical losses, are 8 kilonewton. Okay, what will be the piston speed in the positive or negative direction? So we have to calculate both speeds, and how much pressure is to have exerted on the surface of the piston to make the positive movement. Okay, so what is the useful power in the positive movement, and what is the total efficiency? So the solution is very simple. We can calculate the speed of the piston with this little equation here, which we covered before in pneumatics and in hydraulics as well. And yeah, so we have to calculate the surfaces, so the positive chamber's surface and the negative chamber's surface, because we will have to calculate the speed in the positive and negative direction, and we have to use the positive and negative chamber surface for that. Okay, it's very simple. You can stop the video if you like, if you want to see. So we have the speed, and I know that if I want to make some how to say, some force, I have to use pressure with these applications. So P equals F per A. So we will move the cylinder in the positive direction, and I have to have 58 kilonewtons. Okay, so this is the force I have to provide with pressure. Okay, so the friction, which is here, Fv, and the real, which is 50 kilonewtons. Okay, so therefore we can calculate the force, but so we can easily calculate the needed pressure to achieve this force here, like this. Okay, P equals F per A. Okay, so 58 kilonewtons divided by the area of the positive chamber. So we can calculate how much this will be, and I know that the output power is basically the force times the how to say it, velocity or speed of the piston. Okay, so the output force, which is the usable force, is 50. Okay, so not 58, because 8 is to overcome friction, times the speed of the piston, which will result in 3350 watts, and we have to push in that much power. Okay, so Q times P, because we are calculating a hydraulic thing. So Q times P is the hydraulic power. Okay, so we calculated, or we have the ingoing how to say it, flow rate here, and we are not calculating with the volumetric losses, so we are excluding the volumetric losses because it's easier now. And we calculated the pressure which is needed, so we can calculate the ingoing how to say, power, and we can see that more than 500 watts is transferred to heat, so it's not very efficient. Okay, so the total efficiency would be the P out over P in. Okay, which will result 86% of efficiency. So guys, that would be the first how to say, practice. I hope you learned something, and you will learn it for the test, because it will be very important in the test. So guys, please exercise them, these exercises, with other numbers and so on. Okay, and with these numbers as well, and you should bring your calculators with you to the test. Thank you very much. Have a nice day.